The Walrus and the Carpenter. Most of us would think we could quote a verse of that if we tried, and yet again I think some of us have forgotten. Alice, would you bring us up to date again with the Walrus and the Carpenter?
The time has come, the Walrus said, to talk of many things, of shoes and ships and sealing wax, of cabbages and kings, and why the sea is boiling hot, and whether pigs have wings.
Thank you, Alice. Perhaps you'd like to hear the engineer's version of that. A simple parody. The time has come, the speaker said, to talk of many things, of trains and trams and fairy tales, of lines of force and things, and gyros like inductances, and then magnetic springs. All these and more we shall do this hour. Fairy tales, did I say, and lines of force. I want to tell you about fairy tales and what becomes of them when you grow up. The fact is we all continue to believe in fairy tales all the time, but of course we give them a much cleverer sounding name so that it won't sound childish. We call them analogies. Another name for fairy stories. Now, a lot of fairy tales were designed to point out morals one way or the other, like don't be greedy, try not to put yourself first, and so on. In a way, the analogues are the same. You invent a story that sounds as if it could be true, to try to understand, if not only in part, something about things like electricity and magnetism that would otherwise be quite impossible to handle. So we say electricity is like water flowing in a pipe, and at once we have a feel for an EMF, an electromotive force. It's the electrical pressure. And because you understand water pressure, you know what it feels like, you begin to understand electrical pressure. Fairy stories, nothing more, but very, very useful fairy stories. Just as it doesn't do to ask how the pumpkin changed into a fairy coach, one must not probe too deeply into analogues, or they tend to disappear in a puff of smoke like the traditional wizard in pantomime. Let's think about lines of force and things. What is a line of force, said Alice. She didn't, but she might have. And the good book says, with confidence. A line of force is the direction in which a free north pole would move. Fine. Oh, so they're not real then, says Alice. They're just directions. They're not real. Well, no, said the White Queen, but they're in your head, though. Alice tries another approach. She said, what is a free north pole? Well, a free north pole cannot exist. Not a very useful thing, then, is it? Said Alice. Wrong again, snaps the Queen. I've always found it most useful. So have you and I, so long as it gives us the right answers. But when it gets to asking us whether, if one looks at the lines of force from a bar magnet, and I confess I think that most of us think of the lines of force from a bar magnet as being displaced only in a plane, because we see them on a piece of paper in a book. But if you could see lines of force in a magnet, and we try to, we got our thing, we often try to look at lines of force as if they were piles of iron filings. And there, of course, lies the danger, because if the strings of filings ever become in your mind the lines of force, then the lines of force will receive a treatment as if they were the real things, which iron filings are, and yet the lines of force are only in your head. Here is a representation of a bar magnet. The experiment that then becomes difficult is this. If we see lines of force sprouting like bristles from a brush, if I rotate the bar magnet Do the lines of force actually go round with the bar, or do they stay where they are and let the magnet spin in the middle? Now, I've taxed my ingenuity and found it possible to devise two experiments, one of which demonstrates quite clearly that the lines of force go round with the magnet, and the other one demonstrates equally clearly that they do not. Well, it was only a fairy story after all, you see. And when you get to a situation like that, there is only one conclusion. If I can quote Sherlock Holmes correctly, when all the impossible things have been eliminated, however unlikely, that which remains is the most probably true, or where's that effect? When you eliminate everything else, if you find that that is not so, you can have it either way, there is only one conclusion left. There are no lines of force. They were imaginary. They were fairy tales. Well, of gyros, like inductances, that was a thought to conjure with, wasn't it? I have a little finished business with gyroscopes, because one of my animals last week failed to operate for me. And when my animals don't earn their keep, I tend to make them work rather hard. It was what I call the demolition experiment, in which we're going to show that a gyroscope, once again, well, another further demonstration that a precessing gyro does not have angular momentum, what is commonly known as inertia, and yet the same speed, if it was not spinning, would demolish that it could not demolish before. So first of all, we'll spin up. We've got this rod. The mistake we made last time was to put it through a hole. This time we've clamped it really tight. Okay, Bill. Let's go. Oh, yeah. Hang on. Here we go. Did you see that? As soon as it touches the rod, it drops like a stone and returns. It has not the inertia to knock that off. So now we clamp it and we turn. The other thing we didn't do last time was to make sure that this baseboard was firmly secured against something to make it like a hard wall. If you don't do that, then of course everything gives way. Spin it from the top side. Now we have calculated, you saw me blowing a note there on the recorder. That was so that I could listen to the note of the wind over the Pelton bucket, so that I could get the speed appropriate to the angle which I am now going to drop the gyro from. When it lines up with that shadow there, then that is the correct height to give the same velocity at the bottom as we hit it before. And this time, I hope, fingers crossed, not quite. Once more. Now, you can work out the sums and find that the velocity was the same. Well, now, before we finish with that gyro, I have another couple of demonstrations which are going to lead on to something else. With the handle at the back, I can get a contact with the gyro. If I push the handle in, I can then rotate the gyro by hand. And if I do that, when it's spinning and it's released, it will rise up. As you saw last time when Dennis was holding that thing and I turned him faster, it rose in the air. When this one rises up, there is a piece of rubber tubing on the end of the shaft. The shaft is spinning, and when it hits the ceiling, it will try to take the gyro around even faster, which means that the gyro will press even harder on the ceiling. You'll be more sure of getting a grip, and so on. And when a gyroscope is force precessed in that manner, in other words, you demand a precession rate which it can't give you, and yet you stop it from rising as it wants to, it ceases to be, in my world, it ceases to be a gyroscope at all. And the fact that it does so will be reflected in the behavior of this trolley, because you'll see it begin to shake it about like that eccentric drill shook me about. but not until the rubber hits the ceiling. Let's have a try, Bill. As I said, docile as a lamb, no momentum, no centrifugal force. Let's wind it up. There she goes. Bring it down off the ceiling. Whoa, steady boy. Docile as a lamb. We're not through with him yet. We're going to make life harder. We've made the ceiling slope. Now surely, when he's at the lowest point, that's one thing. But how does he manage to climb up on his own? Can he climb up on his own? Once more. There he goes. Sorry. There he is. He can climb as well as fall. Whoa, he's lifting the whole lot up. Okay. And here he is saying, look, I didn't do it. Not dangerous at all. I was going to say to you, can you see the lid bending under the strain? You didn't need to. He chucked it right off in the end. Now this is only a lead-in to a Victorian toy which was brought to my notice during the earlier lectures, which I hadn't seen before, and through the kindness and courtesy of Mr. Robert Bentall, who I'm glad to say is with us today, he brought me along the best executive toy I think the world has ever seen. This one is a real oldie. It's a gyroscope, it's a cone, you put on top of a pivot, and then you put into the top holder, should have done that first, a piece of wire, a piece of brass that's been bent into a zigzag pattern. Now, locate the gyro. And this time you don't need a motor or string or anything. You just need your finger and thumb just to give it a little spin. Then you displace it, and then you lower the top piece and get the gyro feel of it. Have a feel of it. And there you can see it running round both. A little bit lower, I think. Better. Go on. Not just round one side, but right round the end and back. And so on. And it runs very, very slowly before it finally loses a grip on that wall. This is the ceiling experiment turned through 90 degrees. Well, of course, that's an interesting demonstration, but there were variations on it. Here is another piece of brass strip made like the petals of a flower. This, in a way, is more remarkable still. So, just a little spin with the thumb and finger, then deflect it to one side. There it goes on the... Oh, steady. That's ready. Why wouldn't you like that? A bit lower. It's better. No, sorry, too low. Fresh spin. Hold on. Round the inside of the flower. I've missed him. I've got you. round the inside, round the outside. Now, surely every executive, when it's running too slowly, it does that. It says, hey, I want a bit more juice. Now, I'm sure that these are going to find their place on the mantel shelves of managing directors' boardrooms as well as in every school in the country, I hope, because they're fairly easy to make. There is nothing electrical or magic about that. That is just the plain action of a gyroscope. So, come on. He's not behaving so well this afternoon, this fellow. But if you really want to be a one-upman, you don't just have the petals of a flower to run round. You do your own caricature of your face. Or if you wish to get well in with your favourite cabinet minister, you do his profile in a piece of brass. I'm sure he'd love to have that on his mantelpiece. I know I would. I'll be making one of these, Mr. Bendall, as soon as these lectures are over, with many, many shapes, and I'm sure you will too. Now, last time I told you I would give you the solution to why this spoked gyroscope seemed to behave in a different manner from those we'd seen earlier, in that when I get it up to speed, I can give a twist to the inner ring, and the inner ring seems to be ready to go on precessing, apparently. It slows down as if there wasn't a wheel on it. And I told you I would give you the reason for that. This would be very difficult to understand if we didn't show you a simpler version first. It is what is known as a rate gyro. A rate standing for rate of turn. This is an instrument so common that most aircraft have them. You've seen this gyro before. We've modified it in that we've clamped the outer ring. So the outer ring may only be rotated by rotating the base. And between the base and the inner ring there is a spring, and I've put a stop on the inner ring so it can only go that far, and a pointer. Now, I'm going to turn the whole turntable, and you are to watch the pointer and imagine that it had a scale up here registering the height of the pointer. The pointer is going to indicate to you the rate of turn of the turntable. Spin him up. The rate of turn, wrong way. The higher the pointer, the faster the rate of turn. Stops dead as soon as it hits the base. Doesn't matter whether or not I'm rotating it about a fixed axis like that, or whether I elect to mount it in an aircraft and say the aircraft is now turning. The other way, no, that way, that's right. If the aircraft is turning, it still goes up. It is a measure simply by the use of a single gimbal ring free. Now, the way this used to be explained to me in my Air Force days might amuse you. They told us that a gyroscope had the properties that when you put a torque on one ring, it precessed the other. Right, now listen, lads. This is a rate gyro. Now, rate gyro, the aircraft tries to turn. As it does so, it puts a torque on the outer ring, precesses the inner. The inner ring precesses, stretches the spring. That puts a torque on the inner ring, which precesses the aircraft. Right. But you see, it sounds ridiculous put like that this inner ring could precess the whole aircraft. But yet, when we began with gyros, you couldn't think of them in any other way than that the applied torque produces the precession. And if you go on with that, you finish up saying that that spring turns the whole aircraft. And soon you have to go through the mirror and say, oh, it wasn't like that. It is the precession which gives rise to the torque. The aircraft is going to precess whether this gyro likes it or not. It's going to turn. And this gyro will then demand that a certain force be put on the inner ring in order to keep it where it is. And the only way it can do that is by stretching the spring. So it is the movement that produces the torque. In most of the gyros we've seen, it is the torque we think of as producing the movement. I want you to see that both those things are valid whenever you want to use them that's most convenient. Or again, with Humpty Dumpty, when I use a word, he said it means just what I mean it to mean. Magnetic springs, yes. First of all, though, an ordinary spring. This is just a coil of steel strip. No doubt some of you have got these things because they have been manufactured commercially as toys. They will walk down stairs. Sometimes they miss a step like I do, but there's one. Core, 2 at a time. Once more, Bill. Oh, very dainty, yes. Well, our bedrock for this lecture, and if you can remember it for the rest of your life, your bedrock is analogy. It is fairy stories when all's said and done. And we shall try to put analogies together like we put jigsaw puzzles together. It is the unfilled holes which are liable to lead us into fresh pastures. Could we have the blackboard, please? I claim that when I'm thinking about a different thing, I've transported myself into another world. In the electric world, you teach these things at school. I'm going to put ticks opposite these quantities which are well known to you already. In the electric world, you know that an electromotive force drives a current through a resistance. You learn that for O-level. Now, conductivity is a sort of inverse of resistivity, and if you say that copper is a better conductor than aluminium, and aluminium is better than brass, and so on, you become aware of conductivity. So we know about that one. And then you go into sixth form and you learn about inductance of a circuit, which is a new concept. But that is in all the books. That's well known. I would not have ventured into this world of gyroscopes unless I had had a preparatory training. And in 1966, I produced a mathematical paper on magnetic equivalent circuits, and in the process I got a hold of a new concept for me. That instead of electromotive force you should have magnetomotive force was known to Michael Faraday in 1831. An MMF drives a flux, and it drives it through a magnetic resistance which we call a reluctance. That may not be familiar to you, but it is in many, many books. What is then magnetic conductivity? Oh, look, he's written permeability. That can't be right. It is, actually. The only thing is you were introduced to permeability through the force between two isolated poles, which, as we've said already, can't exist. So it comes in much more naturally as a magnetic conductivity. You should have known about it if you didn't. And when I was doing my magnetic equivalent circuits, I came across the concept of magnetic inductance, to which I, therefore, like when you grow a new species of rose, a new breed of rose, you're allowed to name it. I was allowed to name it. I've called it transference to match up with the other. So this, then, was a most useful adventure, that one. This permeability was a bit of a surprise. And we got other medals we're going to decorate. The thermal world. You can think of heat flow like you can think of electric current flow. In the same way that you put varnish on electric wires to keep them from spilling out the electricity, so you put lagging on water pipes and so on to keep the heat in. And it is temperature difference that defines heat flow. That's that drives the heat through a thermal resistance. And all those are known, and so is thermal conductivity. And yet, then, what is thermal inductance? Well, you put a big question mark there. I said it is the unfilled holes which lead, possibly, to profitable things. And so I embarked upon the idea of an inertial world, where a force, like an electromotive force, these are all expressed in terms of electric concepts, a force produced an acceleration on a mass. Now you can put ticks on those if you like or if you don't like. It depends on what sort of a person you were. If you're already sold on the idea that in an inertial world it is mass which is the effective resistance to the force, and you may or may not agree that those are well known. It's just up to you. But what inertial conductivity is, we haven't yet discovered. And the last one has been given a name by the American mathematician W.O. Davis, called it intractance, and I'll go along with that because it fits in those other words. And this one has been seen already to be an exciting adventure. Not just merely useful, but this is the one we've been doing now. I want to emphasize to you that some of these experiments, especially the gyro ones that I was showing you last time, are not things that I've done for years and I can repeat them ad lib. The reason I didn't smash that stick last time was because I was doing it for the very first time in front of you. I'd not even tried it before. Because when a person's done an experiment 500 times and he's doing it again in front of a class, it's as dull as the proverbial ditch water. You can tell by a man's eyes when he's excited as well because he's doing something he's not done before. I don't want you to go away and think that all this science is what you should have known, it should have been in the textbooks and so on. We are making the science as we go along. And we are making this intractance, and now we are going to make thermal inductance. We're going to see what it looks like. We've got an experiment in front here which involves a copper bar which has been thermally insulated with asbestos tape to keep the heat in. And we're going to dip this end of the bar in a bucket of ice. And we're going to light a Bunsen burner under the far end. And we're going to cause a heat to flow along the bar. And we're going to measure the temperature difference, that is, if you like, the voltage, at 5 points along the bar. And when the heat has been flowing for some time, we're going to take the Bunsen away and swap ends and put the ice on the other end. Because I want you to see what thermal inertia really is. We want to be able, before we go home, to fill in that space and see what it was. Now, I have a team of observers, trained observers, sitting in that row, and when I call out their number, they're going to come and read the thermometers, which those voltmeters are, and they're going to chalk up the score on the artificial painted thermometers on the back so that we can see the state of play in the temperature along the bar. Have we started to rise at all, Alan? We have. All right, we'll just do the exercise ones. Number one, would you come and read and record?
38.
38, come and clock it up. Number two. 28, clock it up. Number three. 26, number four. 27, number 5. 24. You see, the ice is beginning to have an effect on this end. It's pulling it down. The Bunsen is beginning to raise the other end. Thank you very much. Back you go. We'll call you again in another couple of minutes and see how the heat is progressing. Now, in electromagnetic terms, I told you that they were a circular affair. I said gyros are a circular affair. So also are electric and magnetic circuits. This is my model of every electromagnetic machine, every electric motor and generator that ever was or ever will be built. It is a representation of it. You have an electric circuit, generally of copper, and a magnetic circuit, generally of steel or iron, and the two are interlinked. It is all a question of how many linkages you can make and break that determines how the machine works and how well it works. Well, of course, you try to get the maximum current for a given EMF in this, and you try to get the maximum flux for a given MMF in this. So resistance and reluctance are your arch enemies. So you want these loops to be as short as possible and as fat as possible, and that shape appears to have achieved almost the ultimate, because the whole of the hole, if you see the difference in spelling, the whole of the hole in the donut of one is filled with the other and vice versa. So that is the best electromagnetic arrangement you can ever make. No, it isn't. It is all a question of ingenuity and topology. An engineer is, in French, an ingénieur, an ingenious one. You say, I can do better than that. Melt that copper down and smear it all the way around the steel. It'll look like this. This is a bigger one. Interesting shape. Where's the steel gone? It's on the inside. Now, you see, the steel is not in the center, so to speak, of the copper, because you need more copper in the bottleneck through the middle. That is perhaps the best one can do. You could, of course, have elected to smear the steel around the copper. And no man alive has ever been able to smear them both round each other at one and the same time. Thank you, Bill. The other thing is this. What happens to an electrical machine when you make it twice as big? These rings are twice as big in every linear dimension as the first set I showed you. Their resistance of the electric circuit, the reluctance of the magnetic, are doubled because their length is doubled. But their areas are 4 times as great. So the resistance of that is twice for twice the length, 1/4 for 1/4 the area. It's half the resistance it was before, and that's half the reluctance. That machine, I would say, is 4 times better than the other. And you can have that betterness either in cost price or efficiency or power factor or anything you like. Now, we've talked about linkages, and we've talked about sorry? Oh, we need a reading. Yes, come on, number 1, quickly. Things have happened. Right off the scale, put it on the board. Bill, take the Bunsen away. Number 2, read.
84.
84 on number 2. Number 3, that's right up to the top. That's 83. And the next, 83, down a bit. 30. And the last one. And will you take the Bunsen away now? 23. Yes, we need to take the Bunsen away now to get the... But they'll come up without, yeah. We need to remove the source of heat and put that last thermocouple back, if you would. Barry, would you put... Okay. Now we've got a progression of heat. If we could see that when it's right off scale, it's coming down rather like that. And now we've taken the heat away from that end, and we're going to put the ice pail under the other. You need boiled him alive. All right. Meanwhile, I want 2 more volunteers, because I'm going to show you how this tubular motor is wound. Yeah, you two will do fine. I want you to take this wire, and you'll stand one behind me at each side. Try and find the middle. About there. Will you hold that end? You hold that end. And will you go stand behind me now and sort of pull fairly gently. And I'm going to wrap the wire under the bar. Fine. Hang on to it. Now you see we've made the sort of winding that you have in this tubular motor. Because here we've got current going clockwise and then followed by anti-clockwise. So we've made a north pole and a south pole. Now we said when we had 2 knots in a piece of rope that a left and a right-handed knot didn't make a nothingness. But if I take that off there and they pull, there is nothing. So sometimes, thank you, a linkage is not what it seems. Can you come and read again? Things will have happened fairly vigorously by now. Come and read your number 1. Sit right off the top. I wish we got it back in right, Alan. Couldn't. It's all right. Number 2. Leave it alone then. Number 2.
That's about 103.
103. Isn't this strange? We've got ice in that end now, and the temperature in number 2 is still rising. Number 3.
52.
52. That's gone up as well. 3. Yeah. 103, go up a bit, that's it. Stop.
37.
37 on number 4. Number 5. 25. So you see they're still all rising apparently. The first one is probably started to descend, but we can't read it yet. Okay, thank you. Back you go. We'll have another go in just a minute. Now this tubular motor is going to be my magnetic spring that I promised you. It is capable of throwing in the air little slugs of metal like that, which consist of a number of rings of copper and steel alternate on a steel core. Are we at the right voltage, Barry? The top piece is here. Now this little slug, I drop him in. He says, I want to get out. Oh, let me out. Do you notice he's hitting my hand all the time? He says, I want to go higher. All right. We'll let him go higher. And if we've done our sums correctly, he will not be able to get out of the top. The suspense. Now, this one I've done before a lot of times. We've got him more or less nailed there. You would think there was a beautiful spring inside there, wouldn't you? And yet you know it can't be a spring because the amplitude is getting bigger. A spring would have brought it to the top by now. It would become a damped oscillation. This one is an obviously reasonably stable oscillation. And in case you think that I have got a spring in there just to help, oh, is it getting there? That's Barry twiddling. Yeah, all right. He's just trying to make it look out of the top, aren't you? Go on, have a go. It's nearly there. Just require, actually, to get it out of the top, you require a lowering of the supply voltage. Not a raising, but a lowering. There's another thought of a 180-degree reversal. No, it doesn't feel like it today, mate. It's not going to come out. But if you think there's a spring at the bottom of there, we'll soon show you that there isn't. There's a dull thud at the bottom, and of course I can get it out. Well now, can we take another reading? Number 1.
64.
64. Come and mark it up. Number 2. As fast as you can now. Number 3, start off.
48.
48. Number 4.
49.
49. Down a little.
42.
42. His has gone up, you see. Still going up on the left.
31.
31, extreme right. That's gone up 2 or 3 degrees. I think that probe must have gone in a little bit differently on the second time. It should be lower than this one by now. What is it now? Would you read it?
About 58. It's still dropping.
Still dropping. I'm surprised it's not dropped below this other one. 58, okay. That is the state of the parties now, and I think you can begin to see what's happening. This lot is going to go down to 0 with the ice, and meanwhile some of these over here are still rising because they see a higher temperature in front of them, so to speak, and we have succeeded in generating a thermal wave. We've got a thermal wave which is progressing along that bar, and now you can see why you weren't taught this, is because it isn't very useful when you've got it. It was an investigation, a curiosity, but I think we've gone far enough already for me to be able to write in just what we can put in there as thermal inductance, because it's known to you by another name. What is it due to? It's due to the thermal capacity of the bar. The bar's ability to retain heat, even though that end has been put in ice, and to pass some of that heat both ways. So it was our old friend thermal capacity and nothing more, and it was therefore not very interesting. That is one of the processes of inventing. You must go along filling in the spaces and seeing whether or not when you fill them in you can explain them. I'm not sure that this is going to be an awfully profitable thing to investigate, not as profitable as that one, but nevertheless it'll get done in the fullness of time. How's the first temperature now? Is it About 46. And the second? About 42. That's not changed. We'll have a look again in a minute. First of all, we're going to show you one of those jumping slug things, but only going one way. We're going to make gravity bring it back. This is a electrogravitational spring, then, for want of a better name. And the missile has gone up slightly in size. It's 2 pounds, 2 pounds of steel with iron, with the copper wrapped around it. And this time, the coils are wound in a different way, so that at the bottom, you've got thin coils, and they get fatter as they get higher up, which means that the magnetic field is accelerating from the bottom, going faster and faster. And I'm going to ask Mr. Coates if he'll catch the missile in a bucket. Would you muzzle load it, Barry? That's right. All right, he's going to try and catch a missile. 3, 2, 1, fire. Wow. Well, the hell's that? They'd like that one again, I think. Ready, fire. I wanted to do it twice to show you the accuracy. This thing can put it, if a fly had been sitting there after the first drop, it would have hit it on the second drop. This gun is extremely accurate. Things never fall upwards, said Alice. Well, I can show you something that will give you a jolly good try. If you have a coil of wire and you connect it to a source of alternating current, if it happens to have a sheet of aluminium on the top, it doesn't sort of care for it much. It's inclined to get rid of it. And you can make it, by suitable practice, come either that way, or, which is more difficult, with crossed hands that way. Dropped it. My right hand's not as good as my left today. But of course we could also take it straight up. You notice it's only when I'm putting it on there, straight up. And I can make it, I believe, turn a somersault. Won't you? Yeah. Lovely. Now, the question is, will it float? Well, it'll try, but it's not going to make it. It's like balancing a pencil on its point. We'll have to be content just to see it jump. Unless we decide we'll turn the coil over and let the coil have a look at a big sheet of aluminium and see if it'll float stably then. Oh, yes. Wowee. There's the thing. It's telling me the bench isn't level. That tells me the bench isn't level. But what I want you to go back to is think about Alice, who said that things don't fall off upwards. I have not yet found an electromagnetic device that if it would work one way up, it would also work the other way up. That wouldn't do that. If it won't work one way up, it won't work the other way up. So if I could not float that stably on there, then I certainly couldn't do it upside down. But if this falls off, as it does, it falls off like that. Now imagine you're looking at that in a horizontal mirror. Instead of the plate doing that, it'll do this. It'll fall off upwards. I want you to watch this coil running to this edge, which I'll make the nearer edge. It always runs to the nearest edge and falls off. Now, I want you to see how it falls off. It doesn't fall off like this. It falls off upwards like that. You see what I mean? Steady, boy. Over there, go on. You see? Nose first, as it were. Up. You can't reverse the thing just by inverting it. Well, this coil produces about 5 pounds of lift on there. I can easily push it down. About 5 pounds of lift. Now I want to put a piece of steel on there and see what it does on the steel. This is another of those impossible things that the Queen thought up 6 times before breakfast. There are people in my business still telling me that this is impossible or that I'm cheating. a coil, a piece of steel, and some current, and some nothing. Anyone over here like to try the strength? Somebody, let her go. Yeah, you got big muscles? I want you to try and lift this coil. Try and lift this coil off when the current's switched on, okay? No, you're not going to make it. I can't do it either. You'd have to lift the whole of the iron sheet with it. There is over 100 pounds of attractive force between a magnet and a steel plate, and why not? Let us put the steel plate underneath the aluminium. What a stupid thing to do. You've got to ask silly questions if you want to get good answers. 100 pounds of suck, 5 pounds of lift. Who'll give me the money for 95 pounds of suck? The answer is most people, whether they are qualified electrical engineers or not. Where does that 100 pounds of suck disappear to? Look, right over almost. We now have more lift than we had before. About 10 pounds now to shove it down, and see it get away from the steel. Look, doesn't like pieces of steel. What have we done? We have made of the aluminium a mirror. The current in this coil is reflected in an opposite current around the aluminium. So it's like looking into a mirror. You get opposite currents which repel each other. When you put the steel under, it is as if you had cleaned the mirror. Putting the steel on is just like cleaning the mirror. Can you see the analog creeping in? You can understand why cleaning the mirror makes it easier to see. You can't understand that, but if you remember the mirror and the cleaning of the mirror, you'll always know that steel at the back of aluminium makes the aluminium appear a better conductor than it really is. This isn't superconductor in liquid helium, and she's ordinary aluminium with apparently a bigger conductivity than copper, a sort of hyperconductor. Now we're going to see if we can fool this old coil. Bring up the sheet, lads. We're going to give it some artificial edges to have a look at. Extra conductor, it says we get more lift still. But there, you see, we've left a pair of crossed slits. We want to see what it thinks about those and what it thinks about the rabbit hole there. Okay. I think better on a bit lower voltage. Up you go. Oh, yeah, look. He likes that. He says, yeah, I'd like to stay looking at that. Well, what about this one up there? Have a look up there, see what you think of that. Oh, he touched his cap to it, did you see? He goes by. There it is, look. Look, there's a hole. Oh, my. There's a hole. I found the hole. Now, some years ago, people have been started to study high-speed transport possibilities with linear motors. A linear motor I've shown you in an earlier lecture. You put a piece of aluminium on, turn up the juice, very wrong switch, and away it goes. If I really turn up the volts on this, I get something else besides push. I get lift, and it will literally push that through the air, you see. Look, fellas, no hands. But if I put it, we'll try a lower voltage, if I put it a little bit on your side to begin with, not in the middle, then it chucks it off sideways. If I put it off my side, put it off my side, it's inclined to push it my way. In other words, it is not self-centering. It is, in fact, self-decentering. Well, linear motors were proposed for a tracked air cushion vehicle. We got as far in Huntingdon in 1972 as this machine, which weighed, I think, about 40 tons, and this succeeded in reaching 108 miles an hour, starting and stopping from rest against a 20-mile-an-hour headwind. That's equivalent to 128 miles an hour, in a mile of track, starting and stopping from rest, which was not a bad effort for a single linear motor. But air cushions went out of fashion all over the world all of a sudden. Tracked hovercraft was closed. But meanwhile, the Americans had invited us all to a tournament in Washington. We were all given 30 feet by 20 feet of space in which to demonstrate a workable system. And we thought if we could get an all-electromagnetic system, this would win over an air cushion and electric motor propulsion system. And Professor Eastham, who was then a colleague of mine at Imperial College, he's now professor at Aberdeen, produced an idea that we could not only lift and push, we could guide as well. In December 1971, they asked us to make this demonstration for Transpo 72, which was in May 72. We got just 6 months. And in that 6 months, we produced this. That is an aluminium trough. I'll raise the voltage. There is lift, suspension and guidance from one and the same set of coils. We called it a magnetic river because it feels as if it was in a riverbed. We dressed it up for the exhibition. We put a top on it and made it look like a real vehicle. And of course, we hoped that our American friends would think this was full of electronics. No, and let me say there is no electronics and there's no control gear, just simply one 3-phase cable going in. But here was our exhibit at Washington Transpo 72. Now, you need a target to make you go, you know. And when the tracked hovercraft closure was made final, there was an investigation by government about the closure, and the Select Committee of the House of Commons arranged to pay a visit to Imperial College to see the work we were doing. So we thought we'd sort of put something on for them that was a bit better than that. Although we had a 30-foot track for Transpo 72, we built this track, which they're going to bring on now. And at once it raises the question in the minds of the critics. You don't really propose putting stuff like that all the way along a 300-mile route. Think of the expense. Well, whilst they're putting that in, try and not pay attention to them. I'm going to show you something else. This is expensive. This is cheap. Piece of aluminium. If instead of using this just to push the aluminium, if I nail the aluminium down to the ground and then switch on the motor, see what happens. Motor's got to go, hasn't it? So all you have to do then is to turn it upside down. That becomes the track and that becomes the vehicle. So with that in mind, I hope you will look upon this track in that same way, that you are looking at the vehicle and the track is 300 miles of aluminium sheet. All right. Would you like to test for polarity? Put the juice on a bit, Alan. Right, that half's right. The other half's right. Right, turn it up full. Here we go. 2 inches above the surface. Woof. They're both the same. Now the top dressing. High-speed vehicles of 1980. On. I'm going to ask Mr. Coates, as usual, to catch it. Well, hold on. One more I think they would like. On again, Alan. There you go, Bill. Now we're going to have a little more fun. You remember the spinning ball and the way that we changed over 2 of the connections? You do that one, Bill. No, we're not going to hit cameraman number 1. He's much too valuable. We've only reversed this half of it. This half is now firing this way, and this half is firing this way. The little sheet first. So we've made a sort of pendulum, haven't we? Magnetic springs and electric pendulums. My goodness. You know what pendulums do. Switch on, Alan. Not very interesting. Off. Sometimes I marvel that the linear motors I make today look so like the ones I made in 1951, which didn't work at all. And I asked myself, well, now, what is the difference? And the answer was, it's in the detail. It's only in the detail of these two sheets. One's wider than the other, nearly twice as wide, a little bit longer, half as thick. The rest of the apparatus is the same. Well, this one behaved like a pendulum. On again, Alan. Isn't going to stop, is it? Okay, off. Now we thought we might conclude by giving Alice a ride. She's mounted as for a toboggan ride, and we let her face camera one, and here we go. On again, Alan. Higher up in the air still this time. Oh. Okay. Electromagnetism is like gyroscopes. There are new things all the way if you look for them. Next time we'll be talking about invention. I'll tell you about how one or two of these things came to be invented. And meanwhile, I think you'll agree that this is no ordinary electric motor. And some of those other things are not ordinary spinning wheels. So we'll close by giving Alice another ride in a moment. Meanwhile, join me again next time. Okay, on Alice.